That's the current reading. Gasoline, very short life. So that's synthetic oil. Yearly synthetic.
All right. Well, I'm going to turn my screen off. Hi, everybody. I'm delighted to share my experience with you, and with that, we'll get right to it. Let me see if I can turn my camera off without screwing anything up. Okay. So today I'm going to focus on what Jonas has described, the Ultra-Violet Optical Screening Tool for UVOST. And it's generally for NAPL investigations. It's not for the dissolve phase or the vadose zone or vapor phase. It focuses on NAPL, the source term. First of all, I'm a chemist. I'm a spectroscopist who studies light and how light interacts with chemicals. When it comes to geology, I'm a little bit of a deer in the headlights, and I don't know if you guys have that colloquialism down under, but in general, I tend not to know a great deal about geology because I never studied it. But I've picked up quite a bit, enough to be dangerous and probably butcher some terms. So please forgive me. When it comes to what I'm going to be talking about today, you folks are going to get a little bit of that deer in the headlights feeling that, boy, I'm overwhelmed, right? But my goal here this morning for you folks is to just plant some seeds. You know, I really want you to understand that you've probably got things in your data set, or you could get an NLIF data set, and you won't know exactly what it means, but there's going to be a lot of information in that data, and I want you to understand some of the capabilities. Okay, so I'm always here. Jonas knows where to reach me. You're going to know where to reach me. And in this day and age, we can discuss data from anywhere, anytime. So feel free to contact me. So if this whole non-aqueous phase liquid characterization, right, releases underneath the ground, if it was easy, you guys probably wouldn't be attending this particular presentation. And it's been so difficult for so long, I was actually gutsy enough to write this title slide for one of my presentations back in 2011. Because at that point, I had seen hundreds of conceptual site models of where they thought the NAPL was and wasn't, and they were always wrong. And in a lot of cases, dramatically so. So I thought I'd have a little fun. I went to an AIPG conference, a professional geologist, and I started telling them how wrong they were about their NAPL, and they admitted so, because it's so hard. The heterogeneity of the NAPL makes it very difficult to understand that distribution correctly unless you get high resolution tools involved. Now, especially if you're going to start relying on monitoring wells, and one geologist here in the States said monitoring wells are holes in the ground that tell you lies, especially with regard to where the NAPL is at, whether there's NAPL there. Okay. Now you can't design a remedy for these NAPL releases without knowing where it is. And a lot of the groundwater tools like wells, they just lack the qualities, the specificity or the coverage. And wells are okay for measuring the symptoms, right? Is the water impacted, but not the disease that's causing it. And that's the non-aqueous phase liquid or the fuel or the oil, the source term. Here in the States, we spent a lot of time fixated on this floating pancake model, which generally speaking, we understand why they would put something like that in a textbook. But the fact is, most sites, it isn't as simple as it's just forming a slick on top of the groundwater table. I've got a great, by the way, if anybody wants this presentation, they should get a hold of me. That way we've got a direct line of communication for later if you end up generating data. But several regulators have really found that, you know, they've written some great articles, and this one in particular, it just really helps to relate to regulators or how regulators have viewed technology like this and how it's changed the way that they approach trying to remediate some of these sites. So LIF is useful. It generates these beautiful, accurate, and I am not kidding you, they are incredibly accurate maps of where your non-aqueous phase liquid is, and it can do it in just days, 4 days in this case. Okay, and it's amazing, but unless you're prepared to deal with this onslaught of data and then in turn actually have confidence that that data truly represents the NAPL conceptual site model, it's not going to be of much use for you. Okay, so it's very useful, but you've got to understand the data, and the NAPL data has got to be validated, and Jonas knows all about that. So a little trivia moment. LIF is long in the tooth. There's another colloquialism for you that means it's old in this country. It's been around a long time. Okay, so July of '92, the Army Corps of Engineers patented the sapphire, the idea of a sapphire window in the side of the probe in what was called the SCAPS program. The Air Force later went on to fund what was called the Rapid Optical Screening Tool way back in 1995. And my company was involved in that. I was involved in this as a grad student. I wrote all the software, built a lot of the dye lasers and the cone parts and things like that. So we've been at it a long time. The company's been around a long time. And as the commercial says, we know a thing or two because we've seen a thing or two. Okay, so we've made every mistake that you can possibly make, and you guys can benefit from that by contacting us if you have any questions about how to go about these things. So one thing we should talk about right away is we're going to be chasing NAPL. You should educate yourself. What is non-aqueous phase liquid? Well, it's usually some form of or fraction of crude, right? Or crude-like substance. Maybe it's a refined product. And the bulk of a lot of those materials are pretty inane, non-active chemicals, alkanes, straight chain, mineral oil that you take as a laxative is straight chain molecules. So they're not toxic. We really don't worry about those, but they play an important role. They're an important, they kind of provide the swimming pool that molecules like these can frolic in and fluoresce when we try to get them to fluoresce. And those are the polycyclic aromatic hydrocarbons. So it's these multi-ring compounds that are in crudes and refined products that are actually generating, absorbing the laser, and then they're induced to fluoresce. And so those are the ones that we're keying on, but the other parts of crudes and refined products, they also play sort of an indirect role, and we'll discuss that just a little bit. Now, fluorescence, most people know what fluorescence means. Fluorescent jackets, fluorescent clothes, running shoes, safety vests, right? But what they don't recognize is there a time element. So most PAHs want to stay down in the ground state. But when we come along with photons and shine light on those, we elevate those PAHs, they absorb that energy, and now they're in an excited, energetic state. And they desperately want to get back down to the ground state. And one of the ways they do that is they fluoresce, almost like a wet dog shaking off water. They get rid of that energy in order to get back down to the ground state, and that's what we see as fluorescence. Okay, but that takes a little bit of time for that process to work its way out. And there can be a few billionths of a second, or even 100 billionths or 200 billionths of a second for that molecule to figure out how to orient itself and get to the point that it can fluoresce. Some of them fluoresce instantly, some take a long time. And so we're watching a population of PAHs in your fuel fluoresce, and you'll see examples of that coming here. Okay, so that's kind of key to the optical screening tool LIF system, is that they're time resolved. Okay, every one of these systems, including the UVOST, it has a little laser in it. Okay, and the function of that laser is to for just a brief moment create a very intense flash of light, like a flash lamp or something like that. Okay, so for a few billionths of a second, a tremendous amount of energy comes out, and that pulse of light travels through fiber optics all the way down hole and then arrives out onto the soil outside the sapphire window of the probe. At that point, it interacts with the soil, and then there is a phenomenon, including fluorescence and scatter and things like that, that go on. Okay, and there's that whole lifetime business. Some of that light's captured by another fiber optic in the probe. It's brought back up whole, and that's where our instrument divides it into different colors and records the time decay, right? The rate at which that fluorescence appears and then disappears very rapidly at 4 different colors. And that's kind of the measurement in a nutshell. Every laser pulse generates some of this information. And the laser's pulsing at 64 hertz, and we average 64 waveforms. So about every second, we generate one of these time-resolved fingerprints, in a sense, of what type of fluorescence is being experienced just outside the window. Let me give you a little visual. Okay, so we're at our site. Maybe we've got a couple different types of NAPL and maybe even a mineral. Yes, minerals fluoresce. Okay, so we're at our site and we've got our equipment and our direct push. Okay, and here's what it typically looks like. You've got the sapphire window tip or probe on it. You got a little sapphire window, and I can see green, so I know this is a Targhost flavor of probe, which is UVOST's sister technology. And the fiber optics are strung through a rod rack, and you guys probably have seen enough direct push seminars to know how this works. But the operator calibrates it, backs his vehicle up next to the direct push, and they start to slowly, usually at about 1 inch a second, work that rod into the ground, flashing that laser light and impinging that on the soil. Now, if you're not in actual NAPL, maybe there's a lot of vadose zone or dissolved phase contamination, but if you're not in actual NAPL, that waveform is going to be tiny. And we'll talk about more of that in a moment, but very small signals, maybe just a little bit of background soil fluorescence. Okay, well, they screw another rod on, right? He runs the rod across the fiber optics. He screws that into place, and the geoprobe slowly taps that probe down into the soil, and wow, okay, we've all of a sudden gotten into some soil that generates a large fluorescence waveform, is what these are called. And we know it's NAPL. And by the shape, just by the shape of these 4 peaks, I can tell you that it's gasoline, or it's something that looks exactly like gasoline. So they screw another rod on, and we're going down further. And now we're in NAPL again, but we're in a different kind of NAPL. I can tell that by this faster decay rate in the first channel and then these three long, slower decay rates that follow. That's a classic diesel waveform. And if we keep pushing, maybe we push through some sort of calcite, a crushed limestone or something like that. That'll produce a small response, typically pretty measured response, but it is almost always the last three channels look like Neptune's trident spear. Okay, so let's go down inside the probe there. Let's zoom way in on what's happening just outside that window, and we can see laser pulses are being launched. Those laser pulses ultimately just smack the soil right outside the probe. And so you're getting flashes of fluorescence. Outside of that excitation, it's absolutely dark down there. So some of that light ends up being collected and brought back up hole to what's called a photomultiplier tube. Okay, and those pulses of fluorescence then scale with how much NAPL is in the pore spaces of the soil. The more NAPL that is saturating the soil, the taller and larger those responses get. Okay, and remember, this is happening very quickly on about a 300 nanosecond window. Okay, so you've got your excitation. And in fact, this is what the laser looks like compared to the fluorescence. Remember, the fluorescence has millions of PAHs that are getting into the excited state and fluorescing, and then slowly, at least in terms of the laser, they're going back to the ground state. And at some point, there's no more light being generated. Everything returns to darkness. Okay. Now, in many cases, the color of the different fuels, right? Maybe will be in gasoline and it will look like this, kind of a nice cyan blue. Well, diesel is often a nice cyan blue too. So color alone doesn't differentiate, but diesel always has a much longer lifetime than gasoline. Okay, so just based on that time decay alone, we can differentiate the two. But the real power comes when we separate those lifetimes and the different colors. There's 4 different colors, and I'll describe those for you in a moment. But we string those one after the other, 4 different colors, and each are recorded over time, and they all bleed together to, in a sense, make a fast chromatogram in a way of a fingerprint of what type of product, or maybe it isn't a NAPL, right? Maybe it's a false positive, and that's important for us to recognize that and make sure that those signals don't enter our conceptual site model. All right. So every one of your LIF logs then, after you're done, it's literally a library. We stored about one of those every inch. I don't know how many per meter, maybe 30 per meter, right? And those are all stored digitally. And so we have this nice encyclopedia, in a sense, of stored waveforms about once every 2.5 centimeters. Okay. So there's lots of logs, and after the log is completed, the operator can go over to what are called callouts, and he can scroll up and down that library and actually select a few here and there in order to take a closer look. But the software actually calculates the intensity, right, and plots that versus depth, and then in the fill color that we use to fill the response is actually derived from the shape of the waveform, right? So if it's a blue or a 350 nanometer UV dominant waveform, it'll put a lot of blue colorization and then a little less green and so forth, and it's almost like fingerprint paints, right? So that's colorized blue. This waveform turns into a yellow, and this one turns into an orange. And the power of that becomes a lot more, I guess, obvious. When you look at a log, you can see there are different fill colors in these different regions, and that tells you just at a glance without even having to look at these waveforms that there are chemical differences in the non-aqueous phase liquid with depth. Now, I'm going to show you a lot of logs, and there's going to be a little bold line here at times in these callouts. That means there was an average. The operator selected this whole region, and this waveform that's displayed is the average waveform across that depth range. And here it even does the math for you. 14% RE with a standard deviation of 17.5. And I'll explain what RE is in a moment. Now there's a whole suite of LIF tools, and that's because NAPLs vary greatly in their chemistry, and one of these tools can't really do a perfect job on all of them. Your UVOST that you have down there is very capable of handling all the refined fuels, diesels, crude oil, and it's still actually going to whisper to you, and I'll explain that later. It's going to tell you whether you've got some of your heavier compounds, but it won't do a linear job of estimating how much you've got. It's just going to tell you you've got it, but it can't really tell you how much. Now they all share the same basic approach, but we're going to focus on the ultraviolet optical screening tool. Okay, so fuels and oils are complex mixtures of lots of these PAHs, polycyclic aromatic hydrocarbons, and that's why the different fuels look different from each other. Is they have a different, it's almost like different types of soups and stews have different ingredients. Well, different types of fuels have different ratios of small to large PAHs, medium size, things like that. And that's why they all look different, okay? And we're gonna skip this color, but remember, Roy G. Biv, remember your rainbow, okay? Wavelength, increasing wavelength is decreasing energy. So your more energetic light is down in the violet and the ultraviolet, and the less energetic is up in the red. Because I'm going to be using the term blue shifted or red shifted quite often, and that just means a shift towards the red end of the spectrum or the blue or ultraviolet end of the spectrum. And the reason I'm going to be mentioning it is because things scale in that direction with fluorescence. The larger the PAH, in generally, the longer the wavelength. So down in the 2 ring, like naphthalene, it fluoresces in the ultraviolet. And you start to get into benzoate pyrenes and things like that, they're in the visible. You can see their fluorescence. Okay? So that's a trend that we take great advantage of. So smaller PAHs, right? Naphthalene dominant, they're going to be dominant in that ultraviolet channel, the first channel of the UVOST. Red shifted things like heavies, like benzoate pyrene, large molecules, they're going to dominate over here on the red end. Okay. And this is a bunch of vials with different size PAHs in them, all fluorescing at increasing wavelength with increasing size of PAH. Okay. So let's look at some actual fuel. Remember diesel, like it's a mixture of a lot of different sizes and shapes. But if we apply that diesel to soil at varying concentrations, they're up here in this top banner, right? A decade series of loading of diesel on sand. You can see if we photograph that, and we used the UVOST laser to provide the light for these photos, but you can see that it becomes brighter and brighter, okay? Now, if we put those exacts, and we took those same soils, okay, and put those on a UVOST, and you can see that the waveform gets larger and larger and larger with increasing pore saturation, and that's kind of the ideal behavior. For any one type of fuel on a fixed type of soil, you're going to get a nice behavior, linear behavior of how the signal increases, the fluorescence increases with concentration. Okay, now what's this RE business? Well, we need a way to scale all these measurements. Okay, so we'll use what's called a reference emitter, and that's a cuvette with some oil in it that everybody across in the world uses this same oil if they own a UVOST. And they all clip that on front, right? And then we measure that reference emitter waveform, or the RE. And the reason we do that is because the signal, you can make the signal on a UVOST bigger or smaller by launching more or less laser light. So we need a reference emitter to sort of normalize all of the signals that we're going to generate downhole. Okay. Now in this case, if I go back here, you can see that the diesel waveform is 4 times larger or so, or 414% of what the RE gave. Okay, so that's how that works. It's a lot like calibrating and the isobutylene that we use to calibrate a handheld PID. And we take it right before every logging result or logging event. Okay, and any old fuel or oil that you put in a cuvette isn't going to work, because then I don't know what an RE means on a site that Jonas did. If he's using a different type of fuel, I will completely misinterpret what 100% or 300% or 12% actually means, because he's relating it to a different intensity oil or fuel. And we use different reference emitters for the different types of products. And one other thing that the reference emitter is used for is to recognize, what if one of the channels is damaged, right? What if there's something wrong with the equipment? We know that a Targhost waveform should look like this. If suddenly one of the peaks starts to drop out, our operator can react to that and make sure he gets it back in calibration. And that's what they'll do, Numac will do with the UVOST, is make sure that it's performing its measurements properly. Okay, so let's look at gasoline across that same concentration range. You might notice that it's a lot dimmer, and in fact I had to artificially brighten it. And look, the waveforms are a lot smaller. That's because gasoline is just less fluorescent. I have to zoom way in order to see that I'm starting to get an increase in signal or fluorescence at about 1,000 parts per million, whereas the diesel could see it down at 10 parts per million. Okay, so it has less PAHs in it. It's more dilute. So it's only a fifth as bright as the diesel is. Now, what if we put kerosene or jet fuel on soil and try to take photographs? What happens? You can't see it. It's blind, right? That's because kerosene and jet fuel won't photograph well because they fluoresce in the UV. They're invisible, okay? The UVOST doesn't have a problem with it. It still detects it because that first channel is in the UV, and it was purposefully put there because we started designing the old rapid optical screening tool, and then the UVOST. They were designed to be used by the Air Force to do military Air Force based cleanups, and they had obviously a lot of jet fuel. Okay, so the UVOST doesn't have a problem with it. Now, if I take all of these percent REs that you saw up here, right, the strength of the fluorescent response or the size of these waveforms, and I plot them all, right, NAPL concentration, how much loading we put on the soil versus the fluorescence response in percent RE, you can see we've got pretty good behavior. The gasoline and the jet, they behave pretty well, and so does the diesel, but the diesel's always going to outperform the gasoline and the kerosene because they contain so little PAHs compared to diesel. Okay, so you have to temper your interpretation of what a certain level of percent RE means. So you have to ask yourself, you just logged a location and you got a 10% RE response. Is that a lot of NAPL, or is it just a light staining of NAPL on the soil? Well, it really depends, right? If you see a diesel waveform where you got that 10% hit, you know that it's fairly light because diesel's very fluorescent. A 10% response of gasoline gets a lot more respect because it takes a lot more gasoline filling those pore spaces to generate a 10% than it does diesel. If that makes sense. I hope it does. Now, if you don't have waveforms, for instance, maybe you're using an OIP or some system that uses imagery or cameras, you're stuck. You're just going to be guessing whether that's a big signal or a small signal because you don't have a differentiator. Now remember, waveforms vary because the PAH makeup of those different NAPLs. So if you look at sort of the size distribution of the PAHs that are in the different types of fuel, kerosene, gasoline, diesel, you can see how that affects the waveform. So in a sense, we're looking almost in a crude optical chromatographic sense. We're just looking at a survey of the type of chemistry that is in these different fuels. Okay, so you've got these different colors, right? Now, all diesels aren't going to fluoresce like all other diesels. There's variation. Depending on the oxygen content, how old the diesel is, where it came from, they all generally have the same qualities, but they do differ. And it's the same with gasolines. Some will start out blue dominant right out of the pump. Some don't. Some have fairly short lifetimes out of the pump compared to some longer lifetimes by some of the others. Okay. Now, remember the kerosene, it's dominated by naphthalene. There are almost no other PAHs in kerosenes and jet fuels. That's why the waveform looks like it does. In fact, most of this fluorescence that looks like it's in the green and orange and red channels is actually just riding on the decay of that first channel. So it's very dominant in the UV. This channel is violet color, this is indigo in color, and this last red channel is blue cyan. If we go over to the diesel, now we know why we see so much blue cyan, because these channels are really, even though they aren't as tall, their lifetime, their lasting, the area that they're producing, the total fluorescence is quite large compared to this first ultraviolet peak. Hoping this all makes sense to you guys. And we don't need to dwell on this, but this is why a camera-based system like Geoprobe's optical interface probe or something can't respond to the jet fuels. The blue pixel, the bluest pixel in a camera, doesn't come over here where that ultraviolet fluorescence is, and that's where the first channel of a UVOST is. Second channel, third, and fourth. So there just is no UV response in a camera, so they're going to miss it. Speaking of false negatives, aviation gasoline, and every country's different. I don't know if the refining process of aviation gasoline is different in Australia than it is in the United States, but this is famously a lame, very poor fluorescer. So if you're out at airports, keep your eyes open. A small gasoline-like signature could mean a lot of aviation fuel. One of my trademarks is I like to lay it all out on the line, and maybe I lay too much information out on the line, but one of the things I very much want to make sure never happens is that one of my tools misleads an investigator on where his NAPLs are or aren't. So I'm very careful to tell you what the limitations are, because you've got to know the limitations of the tool or your conceptual site model is going to be flawed. Speaking of limitations, one of the things that vexes LIF and OIPs and things like that are false positive. Calcites, crushed limestone fill, wood, peat moss, meadow mat, marsh mat, shell hash, you name it. If it's alive or once was alive, it probably is going to fluoresce, even if it's fossilized, right? So here I have a couple different types of sand, some gypsum, couple Q-tips, pieces of wood, and if I put those under a UV lamp, look what happens. This particular sand isn't very fluorescent, but the gypsum and the Puerto Rico sand and even wood. So if you're probing through brush or any type of organic material, it's also going to fluoresce, and you can mistake that. Your assumption is going to be, oh, there's more NAPL. Well, that's not good, right? So you need to be able to recognize that. And like I think I mentioned earlier, one of the things that false positives almost always do is these last three channels look like Neptune's spear, right? They're relatively short-lived and pretty equally balanced. And almost every, so this is sand from Hawaii, sand from Dubai. This is a tree root that we went through in the state of Michigan in the US. Okay, so I'll show you how UVOST actually can help differentiate and point those out to you here in a little while. One of those ways are these cluster diagrams, and we'll get to that. But natural soils are almost always going to cluster down in the bottom right-hand corner. Anything that lies outside this home cluster is going to be suspect. So all your calcites or extremely weathered NAPLs that have practically turned back into soil, those are all going to end up. So this is sort of the cemetery of LIF. If things fluoresce there, they probably aren't worth worrying about. Okay, another thing that vexes the performance of LIF is soil particle size. So here I loaded diesel at 10,000 milligrams per kilogram on 9 different types of soil, and they are all 1% moisture by weight. And we spiked them all, and then we recorded them all, one after the other on a UVOST, and you can see the percent RE, or the intensity or the size of the waveform, was much larger, and I'm not going to dwell on this, for the coarser grain materials, and it really gets subdued when you're in fine clays and silts. Okay, so there is an effect there. Now again, I'm a deer in the headlights when it comes to geologists, but I do know what clay and silt and sand are. Okay, so the different types of soil have different effects, and most of it is due simply to the fact that if you remember those photos, and hopefully I can get there quickly enough, it's these pore spaces, right? Now, coarse grained materials are going to have these large voids where this NAPL can squish right up to the sapphire window. This is taken up against a sapphire window. Clays and silts have such tiny, tiny, tiny particles that they kind of hog up the window, and they don't allow any of these big, beautiful globules to press themselves up to against the window, and the penetration depth is therefore very limited down into that NAPL in each pore space. Okay. So these waveforms are very useful. They contain a lot of information, not only about, right, how intense the fluorescence is, but what kind of fluorescence, what's giving rise to that fluorescence. But boy, does it make your head hurt, even when you're, Mr. LIF like me, and you've been staring at these for 30 years, you start looking at hundreds or thousands, and one site might have 100 logs. Pretty soon you're going to be drowning in waveforms, and it's going to be very difficult to sort of keep it together as far as what's going on. So one of the things we've done is develop what's called lifetime processing. Okay, and the software walks through and it tears apart the waveform into the 4 different colors. And what happens then is that you get 8 different values for every waveform, or 8 different values per inch of a log. The intensity, and that's the color, the wavelength of the different colors of light and how much, and then the lifetime. How long did it take for that light to bleed away or go back to darkness? Okay, why do we do this? Well, here's an example. We took a UVOST and applied a whole bunch of different types of NAPL to a UVOST system, one after the other, and you can see the color, the waveforms, the intensities are jumping all over the place. That's a lot of information to handle. Okay. Well, we want to process all those. So if we process this whole file and generate those 8 values for every one of these readings in this benchtop log that we've done now, and we spray those based on the lifetime on the vertical axis and the color on this x-axis, every one of these different types of materials now occupies a different place on the map, right? Diesels have long lifetimes and they're relatively centered, maybe a little bit right of center of balance. If you think about a fulcrum, right? It's a little tippy towards this side, so it's a little bit left or right of center, okay? Whereas blue dominant jet fuels and kerosenes, they're almost completely in that UV channel, so they're almost completely shifted, blue shifted, and they generally have a relatively long lifetime compared to other NAPLs, so they're relatively high. And that really goes a long way for us to be able to see similarities or differences in one log or from log to log to log across a whole site. Now, good grief, some of you have to be wondering, this is getting awful technical. Why do we bother with this voodoo? Can't we just rely on that fluorescence intensity alone? And I've already given you some pretty good reasons why, but here's a great example. Here's a client wanted to, this was actually a military client who wanted to find jet fuel at their site. So here's one of our logs, and what I've done is I've removed any information about color or lifetime, and all I've put up is the intensity, how brightly it was fluorescing with depth up to 100 feet, 33 meters or whatever that is, okay? So where's the jet fuel? Maybe none of it's jet fuel and this is all just false positives. Maybe all of it's jet fuel. You don't really know based on intensity alone. But now if I colorize it, like I showed you earlier, you might see that no matter how large these signals got, they stayed the same shade of color. And in fact, that waveform was the same over and over. It was bigger or smaller, but the relative amount and the lifetimes in the 4 channels stayed the same, whether it was bright or dim. But some of you might see a different color coming in down here, and so did the operator. Here's that cluster diagram now, okay? This is all of these signals, no matter if they were intense or not, they're the same type of fluorescence, so they cluster in the same spot. But some of the waveforms weren't in the home cluster, and they were down here, and the operator actually saw that and called those out. And you can see that it's actually a hybrid waveform. It's got the long lifetime and UV dominance of the kerosene, and there's not a lot because it's quite weathered, but that's superimposed on top of the calcite waveform, or whatever mineral that is it's fluorescing. Okay, so bingo, that allowed us to target very quickly and easily where intensity alone wouldn't give us the proper information. And in fact, now we're processing the data and we're plotting lifetime, for instance, all by itself, the average lifetime of the waveform. That alone tells you exactly where the kerosene is at amidst all of this chaos of different types of fluorescence going on, different intensities. Because it's a different type of fluorescence, it's easy to weed that out, right? So the line hiding in the grass there was pretty easy to spot once you apply that lifetime analysis. And for a lot of our clients and ourselves lately, that's become an easy button, is using those lifetimes, maximizing their value. Speaking of lifetimes, what's going on here? Here's a product that somebody sent from a well, so they send a sample in, and you guys are welcome to send samples to Numac, I'm sure. And when we ran it in the lab, that's the waveform that we got. Now that's a pretty spooky short lifetime gasoline, but it is what it is. But when we went out next to that well and pushed in the ground, what we found was a much longer lifetime waveform. Well, that's, Randy, you've been telling us that that's a different chemistry. Well, it's the same chemistry NAPL, but there's a third player that is involved here, and I'll show you that here in a second. Okay. Oxygen, molecular oxygen. When we're making measurements uphole benchtop with a client's NAPL sample, right? Oxygen is going to get into that fuel, and oxygen just loves to steal energy away from excited state PAHs. So when we excite them with the laser, any molecular oxygen that's dissolved in the fuel is going to immediately try to wrestle that energy away, and therefore, if it takes that energy away, that PAH can't fluoresce. Now, luckily, underground, if you've got NAPL, you don't have oxygen. That was long ago chewed up by the biota. It's anaerobic, and so the vast majority of circumstances don't allow for oxygen to be in the NAPL that the UVOST probe is going past. But that complicates matters for guys like me, because if I'm going to be demoing or doing research and I want to emulate those anaerobic conditions, I've got to flush that oxygen out of the sample, and I can do that by flushing an inert gas through there, nitrogen in this case, and flush that oxygen out. And what you can't see is I've actually got a sapphire window underneath that apparatus. And so I'm actually able to emulate what an anaerobic environment would be for this particular NAPL soil mix. Okay. So when I do that, something fairly interesting happens. One is, here's gasoline on sand under benchtop conditions, 20% room air, so there's lots of oxygen. It's quite quenched, pretty short lifetimes. Okay, so there's the waveform, pretty short. Lifetimes of 10, 11, 12, maybe 15 nanoseconds in each of these 4 channels. And it's down here on the cluster. Remember, this y-axis is lifetime, so it's pretty low down here for a gasoline, okay? But the minute I turn that nitrogen on, and I mean 5 seconds later, the intensity jumps up, the waveform gets much taller, and what else? These lifetimes get much longer. And so it jumps up on the cluster diagram. Okay, as soon as I start purging it. And then something interesting happened. I decided to just let this gasoline, let that nitrogen keep flushing the gasoline for a whole 15 or 20 minutes. So instead of depth on this log, this is just elapsed time. Okay, so maybe 15 minutes. And this is completely reversible, by the way. If I open up the top and let it, and that's exactly what I did. I let the nitrogen out and oxygen back in, and 15 seconds later, it's back to a short lifetime. In fact, all of your YSI oxygen meters and things like that use fluorescence now, a long-lived fluorescence coupon, in order to determine oxygen concentration. Okay, but what happens if I let that flush for a long time? look at the waveform over here. You'll notice that this blue channel, the ultraviolet one, the smallest PAH channel, is starting to actually go away, disappear. That's because I'm flushing out the smallest semi-volatile PAHs. I'm artificially weathering this gasoline because that's what weathering does, is it percolation and earth tides and things like that. Your gasoline in the subsurface is going to redshift when it weathers, and that's exactly what I'm emulating here. I'm redshifting, and it's going from a blue color to a more green or a yellow because of that shifting. Okay, so weathering is going to move things always to the right on a cluster diagram. It's going to shift the balance of the fluorescence to the right, and it's also invariably also going to shorten the lifetimes, because part of that, remember how important those aliphatic straight chain molecules are, right? Well, there's less and less of that available as I'm evaporating the gasoline too. And so the lifetimes are also getting shorter. How about really old gasoline? I dug around and found some 7-year-old experiments where I had been working, and they ended up plotting over here with a waveform that looks like this. So now even the green channel's starting to get carved out because it's weathering. See that? This sample has been in this jar for 18 years. So I whipped it out and I read it and I plotted where the position was. And where's that on the map? Practically down in the basically the graveyard of the LIF plot map. Okay, so different gasolines in fact all generate this same pattern, but look, it's invariable that when you sweep oxygen out of a gasoline, you go from a short lifetime to a long. And then as gasolines weather, where are they headed? They're all headed back down to that cemetery, but some at a much faster rate than others. Isn't that interesting? That's because the chemistry of different gasolines made by different refiners, different times of the year, are going to simply be different, right? So you've got intact gasoline. They all start out generally pretty closely clustered in the middle of the map here with a generally similar waveform. But by the time they're done weathering, some of them have really taken a shellacking, whereas others aren't shifted by very much. Okay. Now you'll notice none of them get very high, and this is sort of the red zone where diesels get. Okay, now if I was to use gasoline for mowing my lawn and things like that, I'd want to buy this gasoline because it's very weather resistant. If I was going to design a sparging system, I'd want this to be the gasoline at my site for sparging, because boy, look how it reacts to a little bit of air nitrogen or nitrogen flushing. It degrades very quickly. Okay. How about diesel? I ran that same experiment with diesel, and look, it shifts the lifetime up. But what does diesel do for in 15, 20 minutes of airing out? Not much. It's much more recalcitrant. It doesn't evaporate very quickly. It doesn't lose its semi-volatiles. It's more of an oily NAPL instead of a kind of a watery, evaporative NAPL. So very small amount of shifting. And in fact, when we're out in the field, if we're seeing cluster diagrams or degrees of shifting, right? One part of the log looks like that, another part looks like that, another one looks like that. Well, then that's another indication you're in gasoline, because it's the chameleon of LIF. It likes to weather. But if I get to a site where over and over and over again, doesn't matter where I'm finding it, it's the same waveform and there's hardly any weathering, and I'm seeing that short, long, I know I'm in diesel. Here's 7-year-old diesel. So it does eventually weather. It just takes a lot longer, but it's still quite high on the lifetime chart compared to gasoline. So let's take a look at some logs. For instance, here's kerosene. One of the reasons I'm sure it's kerosene, there's a few gasolines that actually can mimic this a little bit, but one of the reasons that I'm quite sure it's kerosene is because no matter if the signal was small or large, it was always the same blue, same waveform shape, and that's kind of a hallmark of kerosene. Okay. By the way, if I take naphthalene, literally crystalline naphthalene, which are called mothballs in my country, I don't know what they're called down in your country, they're illegal now. But if I put those on a UVO system, that's what I get. And it is spooky how downhole jet kerosene looks exactly like naphthalene, and that's because that NAPL is dominated by this family. Now there's also methylated naphthalenes and things like that. But basically the fluorescence is mimicking the chemistry of the NAPLs, and it's up to us to sort of read the tea leaves and read those signatures and incorporate those into our interpretation. So here's a complex field log example. Now I don't necessarily know what this is. I've got an idea, right? But I know that the chemistry is dramatically different in these 3 sections of this. This is all NAPL, right? But I know that the chemistry is varying. I don't know if it all started out like this, and this is the most protected, least weathered part of the body. This is modestly weathered, and maybe this is the most extremely weathered. Or is it a mixing zone, right? From a refinery where we're getting 3 different types of NAPL that have all come together. I got a feeling it's a weathering pattern, but I don't know for sure. I can't remember. It's been so long ago. This is from back in 2009. But it's just in stark contrast to this very consistent homogeneous look. Okay. I'm gonna see. I'm just checking my slides to make sure that I've got enough time. Looks like I'm fairly ahead, or am I way behind? Looks like I'm running late. All right. So one of the things we do is we use multiple logs to kind of see where things are headed, right? So if we have questions about some logs, we're going to look at next door. And so that we'll cover some more of that in a couple of weeks. But that's one way of knowing whether you got a hit. Now you're going to spend time, if you want to bound your NAPL body, you're going to spend time looking at these very small signals. Okay, and one of the things we look for to find out is it NAPL or is it not is we look at those waveforms very, very closely. Okay, and we look for those extended lifetimes and any blue shift. This looks like clay or highly weathered NAPL to me. It's the classic trident with short lifetimes. But these little green guys sticking out, they have the hallmarks of NAPL. And the client who I was doing this with wasn't convinced of my interpretation, so I told him to send me some cores. So the core from up here was blank when I split it and looked with a UV lamp. But as I worked my way down, I started to see little tiny weeps, little pinholes of gasoline. And by the time I got to the bottom, like this signature, and of course this is a core, so obviously we did not cover the exact same material, but we got material that was pinholed. And the NAPLs actually spread out across the cut face fast enough that it's starting to sheen out. It looks bigger than it actually was. But that's NAPL. But they can be very small. So don't let somebody tell you, oh, if it's just 1 or 2%, it's not NAPL. If it's got long lifetimes and it's blue shifted, it's NAPL. Okay. Now this particular location, we also did PID. And you can see the vapors, right? The sorb phase and things like that. They're much, and of course there's some smearing with the PID from the trunk line and things like that. So it's seeing a more broad homogeneous distribution, and that's kind of a classic. It sees both the smoke and the fire, right? We see the UVOST just sees the fire element, the source of the problem. The PID is much better at picking up the symptoms along with the source, if that makes sense to you. Okay. So now this is sort of the latest and greatest. This is how we're plotting all of our plots, and we can put these together for Numac on sites where you want that done. But again, here's that background. This is all natural fluorescence, probably natural or highly degraded. This is natural. And these little green guys are all of these points that left. Now we scale the size of the bubbles with the size of the percent RE. So they're tiny because these signals are quite tiny, just 1 or 2% RE. Now, out at your site, heterogeneity is going to pose challenge for you over and over. And Jonas discovered some of that in his research. So we like to do butterfly plots or duplicates. We like to step over a meter and or less than that, maybe a third of a meter, and push twice. And sometimes the results are quite favorable, right? That's pretty good side-by-side behavior. Other times we get dramatically different results, and this is the cause of great heartache for a lot of people. Number one, they think it's the instrument is not responding properly when it simply went through some soil that didn't have the same NAPL in it on the second push that it did on the first. But that also demonstrates for you you've got real problems if you're going to take your confirmation sample and assume that the soil right next to a log where you got a response is also going to have that same NAPL. It isn't necessarily going to have that. So localized heterogeneity is something you have to control, or it'll introduce chaos into your analysis. Okay, so if this was the confirmation sample, it would have come back without NAPL, a wildly different lab result, right? And stakeholders would be disappointed because that stupid UVOST generated a false positive. It said there was NAPL down here, and we looked at a sample and we couldn't find any. Okay, the opposite would have happened over here. Oh, yay, the lab sample agreed wonderfully with the LIF. This thing sure works well. Well, you've got to make sure that you're doing apples to apples measurements in any kind of, especially in a, this is what happened to us early. We spent 10 years doing demos for the EPA and for the Army Corps, Department of Energy. Nobody, we had to bring cores up and demonstrate, and we learned very early, you're going to introduce chaos and you're going to be crying if you don't control that localized heterogeneity. Right? Okay. Now, oftentimes let's say we've got a well with product in it, and they say, come out and push next to that well. There's a lot of times when we've had to push, here's the well, we pushed here, nothing, we pushed here, nothing, and not until we got on the fourth side of the well did we get a hit, because we found the one little vein of NAPL that intersected the well, or whatever was the cause for it. Only one of those UVOST logs actually was able to barely stab a little vein of NAPL. So oftentimes it isn't a very large feature that's feeding NAPL into these wells. Okay. So if you're looking to validate this log, for instance, by sampling adjacent to it, and then determining maybe how does the percent RE of the UVOST relate to GRO analysis or DRO, you've got to have those controls in mind, right? This log is telling you right away, look at the extreme heterogeneity. It's telling you you've got leopard stripes, you've got places with high saturation right next to inches away or centimeters away from soils with no saturation of NAPL. That tells you you've got extreme variability in the degree of saturation. It's also telling you, look at the waveform differences. Waveform 1, waveform 2, waveform 3, right? They're clustering in different areas. You've got considerable variability in the chemistry as well. Okay, so when you bring that core up, where are you going to take that sample to determine how this sample or this instrument responded? Okay, are you going to take it up there? And let's say that core came from this zone here, right? You're going to have to decide in daylight which soil represents which one of these readings. It's impossible. Are you going to take it here or there? Maybe there, maybe there? Well, you're kind of blind to what was really happening, because what was really happening is there are layers, right, of fluorescence, because there are layers of NAPL affected strata. And where you take your sample is going to have a tremendous impact, orders of magnitude changes in concentration of GRO, DRO, right, with where you took your sample. This, for instance, is intact gasoline, way higher in GRO. This is fairly weathered, or it's maybe even got some incorporation by diesel. You see that short, long, long, long? Might even have some diesel in there. We don't know because we never sampled and did the analytical chemistry. Okay, but the last thing you want to do, is take a sample and then come over here and read one of these percent REs and say, okay, well, the lab result said such and such, that relates to such and such from this log. You stepped over. This is a completely different soil column, like it or not. The thing to do is to take an adjacent soil, split it longitudinally like I did, take the open face of one, send it to the lab for the GRO or DRO, but take the other one and put it back on the UVOST, and that way you're making apples to, you're giving both technologies the same sample as best you can. And you'll get a feel for the heterogeneity, right? How bad is this site? Pretty bad. These weren't all taken on a transect. They're just 5 logs that were generated at a site one afternoon. But you can see very, very tight, incredibly tight features here too, but then it starts to broaden out. This is in glacial till. So you know at this site, if you try to sample and you assume that any sample you grab adjacent to an LIF log is representative of those soils, you assume wrong. At a site like this is the Bemidji test site in Minnesota. This is crude oil that's just slowly oozing and towing beautifully out. Same color, same signature, beautiful. Here I wouldn't be the least bit afraid of sending a sampler down and knowing that from 25 to 35 feet, I'm going to get this perfect cross section of crude oil in my sampler when I bring it up. And a few things. You guys are going to get 60 to 130 meters per day. That's a common question. Most of our LIF vendors, I don't know how Numac does it, but they charge per day. And remember that the spiky logs, those tell you a great deal. And in fact, you get hypnotized into thinking these are layers of NAPL down under the ground, okay? Because we plot in Cartesian coordinates, right? I'm producing a layer just by the couple layers, just by the way we plot logs. Whereas that's what goes on in my mind, but I don't know for a fact that we didn't go through a NAPL body that's structured like that. And the probe just happened to cut right through a couple times through the vertical seam. So you don't really know until you lay multiple logs together. okay? Now we actually have, you know, EC, CPT, HP, and we can work with Numac to set them up with those technologies. But they're basically, we're logging everything at once nowadays. And you can see, as a matter of fact, in this high K zone, that's where we've got our weathered gasoline. Whereas up in this tighter zone, that's where the more intact gasoline, and Jonas has seen some of that in his research. Okay. He can fill you in on that. I think we got started a little late. I've run a little over time now. I'm about to wrap it up. One thing you might worry about is the tar ghost, right? Coal tar, creosote, heavy crude. This is where I wanted to remind everybody that UVOST still isn't going to miss those entirely. It's just going to whisper with some very small waveforms that are going to look a lot like a false positive, but they'll be even more red shifted and even shorter lifetimes, and they'll be landing way over here, way hard. If you ever run into these deep reds, you're going to have to sample there if you're at a place where coal tars, bunkers, and things like that might be on the possibilities list. So congrats, you're all practically LIF experts at this point. In 2 weeks, I'll have some more fun. I'll talk about how we can break up the LIF signatures into separate bodies, right? So maybe your client is really interested in one type of NAPL and wants to remediate that, or is concerned about that, or wants to blame the neighboring property for spilling this one when theirs is only this one, that type of an argument. We'll look at some core photography. And then I'm going to show you some research we're doing on activated carbon, and a little bit of a surprise that we found in that activated carbon actually generates, when it contacts gasoline, it generates extremely blue shifted waveforms. And so I'm working with some states here in the US on figuring out how to go in post activated carbon injection and figure out what's happening there.